Okay, so this is an example where you're going to deal with just a rotational motion for an object that's not a little point object, right? So again, we're going to have to deal with the actual shape of it. Okay, so you have a uniform rod, and it has some mass and some length, and you raise it up so it's attached to an axle on one end, right? So it can't leave that red dot, but if you let it fall, if you drop it, right, it'll spin around the red dot, that axle. And so since it will fall, it will pick up some speed from gravity, right? And we want to figure out how fast the tip of the rod is going. Okay, so I know it's been a little bit fuzzy today, so I'll make sure when we're doing on the paper that we'll pause and stay still for a little bit to hopefully make it see. So, all right, so here's going to be my rod, and it's going to have a length L, and this is going to be the axis, right? And we're going to let it fall down an angle theta. So we're going to raise it up an angle theta. And let it fall down. Now, just like problems we did before where something slid down a ramp, right? Or if you just dropped it into free fall, we're going to want to think about this with energy conservation. Right, which means that the potential energy at the beginning in the gravity is going to translate into a kinetic energy at the end. Right, this is just like what we did before, except what's going to be different is a little bit about how we calculate the potential energy from gravity, and then how we write down the kinetic energy, because we're going to think about rotation instead of something moving in a straight line. So the first thing we actually need to talk about that we didn't spend much time on before is what is the height you need to put in, right? You have some mgh to start. So what is h? So when you have these objects that are bigger and more extended, you need to pick the height from the middle of the object. So this is a long rod, and so you have to pick the height from the middle of the rod. So that's actually going to be the height. It's not the highest point that something gets to, right? But it's going to be the height of the middle. So if I draw another triangle for that, with h on the side, the hypotenuse then is going to be L divided by 2, and the angle is theta. Because I'm only going up the rod to the middle. Then for the kinetic energy, I need to just write down, I want to write this down in terms of rotation now, because it's a fixed rotation. So I need to write down 1/2 I omega squared. And I just need to first, so the next thing I need to do then is, okay, so M is some mass, which are given, G, H, I can figure out from the geometry. I have 1/2 I omega squared. Well, omega is related to the velocity, right, which is what I'm looking for. So that's what I'm trying to solve, right? And then I is something I need to figure out by looking at what kind of object I have. Right, and so this is a rod. And then, so I just need to go back to my chart. And so if it's a thin rod, again, we didn't tell you how wide it is, right? So that usually means you can just ignore it. So that's the thin rod, right? And I can go and look. And there's a couple formulas here. There actually is on this version of the chart, the thin rod about the axis through one end, right? Which is M length squared divided by 3. So that's actually exactly the one I want. But I just want to point out that this one's actually not, as you see, like the other ones, through the center of the object. So you can equally get that I from taking the left one, which is the thin rod through the center, which is ml squared divided by 12. And then if you do the parallel axis theorem to move the axis by L over 2 to the end, then you get the ml squared divided by 3. Okay, so I'm going to need to put that in. So I'm going to go ahead and write this again. So Mg, now H comes from that triangle. So it was L divided by 2, and then it's sine theta because it was opposite the angle, right? And then this is going to be 1/2. And then I was ml squared divided by 3. And then there's omega squared. And then I need to go and I can do some simplification to do the algebra, right? The m's will cancel, mass doesn't matter. This half and this half cancel. This L and one of the two L's on the right will cancel. And so then if I just do a little bit of algebra, I'll get square root, and it'll be G. So I can move the 3 over, and so I get something like 3G sine theta divided by L, all under the square root for omega. Okay, question. Do you swap the mass out for I and Mgh like with kinetic energy? No, because so you don't. You still want to use the mass here because gravity is just dealing with the whole mass. Gravity actually doesn't care really about how the mass is distributed, right? Which is what the I says. So that just stays Mgh. I only do the I when I go from talking about 1/2 mv squared to talking about 1/2 I omega squared. Yeah, and then there was one more bit where the question actually is, what is the speed of the tip of the rod as it passes the horizontal position? And so then the speed of the tip, right? The tip is out here at L away from the axis, right? So V for the tip is just going to be L times omega. And so if I put that in, that would just give me a slightly different expression where now the L's on the top in the square root. So you just get square root 3 GL sine theta. And then for this problem, you could put in numbers, but I'll leave that to you if you want to take the time for that. Yeah, so how do you know that this is L times omega? So in this case, it's kind of like the fundamental relationship that if you just think of the tip of the rod as like one little particle, it's going around in a circle around the axis. And for something going around in a circle, you have that relationship. That the velocity of the thing going around in the circle is the radius of the circle times the angular velocity. And the radius of the circle for the tip of the rod is the whole length of the rod. If you wanted to find what the velocity of like the piece of rod in the middle is, right, you would put an L over 2 here. Because that's the radius for the middle of the rod. Okay, so any other questions about this example? Okay, so why don't we cut it there, and we're going to talk a bit about that was basically fixed rotation.